Hello and welcome to the first installment in our series of webinars on quantitative research methods in Eurasian studies. My name is Denise Mischwitz. I am Program Coordinator at the Social Science Eurasia Council, Social Science Research Council Eurasia program. And today our topic of our first webinar is Understanding and Adjusting for Complex Sample Designs in the Eurasian Context. A few notes on this webinar platform that we're using. First, there is a questions feature. So you should see on the right-hand side of your screen a control panel, and there's a tab where you can send in questions. We are going to break for questions in the middle of the presentation and also have a question and answer session at the end. So please, as you have questions throughout the course of the webinar, just type those in, and then we'll break and we'll be able to go over your questions. So you can be doing that as we go on, and if you have any additional questions at the end, you can then send them in at the end also. Also, there's a chat or messages tab, and if you're having any issues with the audio or if something is going wrong, you can just send me a message and we'll make sure that we figure that out. So today, our presenter is Dr. Jane Zawiska. Jane is an associate professor of sociology at the University of Arizona. She has her PhD in sociology, but she also has an MA and postdoctoral training in statistics. She has designed 2 original surveys in Russia, as well as worked with secondary surveys such as the RLMS and GGS. And Jane is also a longstanding member of the SSRC Eurasia Program Selection and Advisory Committee. So with this, I will turn it over to Jane.
Thank you, Denise. So let me tell you a little bit about my motivation first for offering this particular topic, and then I'll tell you a little bit about what I'm going to do and then get started. I decided to do this mostly because as the main person who teaches research design in my department, I noticed that somehow or other graduate students were getting through to the advanced stages of their dissertations without somehow ever having had training on complex sampling designs. The other reason is that having collected survey data in Russia a couple of times, I've come across issues that I think that the discussion of could be of general use. Now, that said, of course, statistics are statistics no matter where you do them. There's nothing specifically Eurasian about any statistical procedure, but I think that I hope that you will learn the general principles, but also be thinking about how to apply them in the particular Eurasian context that interests you. So my objectives today are to help you to just, first of all, as the user of somebody else's data, be able to identify complex sampling designs and evaluate the quality of samples and know how to adjust for sample designs and statistical analysis. A secondary goal is for you to have an idea of how you might go about collecting your own survey data if you ever had the opportunity to do that. Some of you may have already done that. I say secondary goal because, in 45 minutes or so that I'll be speaking, there's no way that I can give you a lot of detail on that. I'm going to understand I'm going to assume minimal knowledge about sampling designs in this talk so that everyone hopefully will be accessible to. Now, one thing I really want to highlight is this last statement here, which is to understand sampling designs, you need to focus on the process of selection, not on the resulting characteristics of the sample. So remembering that there's always random processes involved. Every sample will be different, even if we've kind of followed all the best practices of survey design. So we shouldn't decide whether or not a sampling design is high quality based on what we get in the result, but rather on the process of selection and whether it follows the principles underlying the probability theory on which we base our statistical inferences. So let me just review the concept of a probability sample. So in a probability sample, elements are selected randomly from a sampling frame. A sampling frame is just a list of all of the elements in the population that we hope is more or less complete. Every element in a sampling frame has to have a known and non-zero chance of selection. Okay, so if you're missing any of this, then you don't have a probability sample. There are lots of other kinds of samples. There are convenience samples, snowball samples. There are times when it's appropriate to use those, but for the purposes of today, I'm going to assume that we're in a probability sampling paradigm. So, and why would we want to do that? Because generally speaking, when we draw a sample, we want to represent the population that we're sampling from. You must have a probability sample for it to make any sense to use inferential statistics, because inferential statistics, which are based on probability theory, which assumes that you have a random sample. So I see all the time papers where people are, running t-tests and reporting p-values and confidence intervals on convenient samples, and I think that that is nonsense and shouldn't be done. So I'm going to assume that we have a random sample of some type. Now, there are lots of places where error can be introduced in the process of sampling. So I'm going to be talking about just one place where the error can be discovered, which is what we call sampling error. So it's a sort of confusing term because the sampling error is specifically moving from the sampling frame to the sample. But this entire process is required to get the survey statistic. So just briefly, coverage error is when you don't actually have complete information or you have incorrect information about who is in your population and the list from which essentially that you sample. And that's a very common problem. If we have time, I'll talk about it toward the end. When I'm talking about today's sampling error, I'm talking about the process of getting from the sampling frame to your ideal sample. It is those people that you, or institutions, whatever your unit of analysis is, that you have sampled and hope to contact. Now, we know that we don't always manage to contact everyone that we hope to, that we draw for our sample. That's called non-response error, and again, that's a whole separate topic. That's actually one of the things I was thinking of doing another webinar on, but we won't have time today. And then there's the adjustment error. There are various different ways of going about adjustment, but the one thing that I'll be talking about today is how do you adjust for the sampling design. If you don't adjust properly for your sampling design, then you will introduce adjustment error into the process of calculating your survey statistics, and your results will be wrong. Okay, so again, what is sampling error? So again, keeping in mind that I'm talking about the entities that are selected into our sample. Okay, so normally when we talk about a sample, when we're using some data, what we have in mind is those particular elements that are in our data set. But here I'm sort of at a higher level of before that, where we're talking about how you go about deciding who you're going to approach to be in your data set. There are two types of effects of sampling error. The one that is less concerning, but we still need to understand and adjust for, is random error. That affects your standard errors. And systematic error, which is more concerning because it introduces bias. So this is where you would get a bias in your point estimates, for example, your estimate of a mean or of a regression coefficient. So the fundamental problem with the way that many of us have been taught and use statistical techniques is that we assume that we have a simple random sample, which we actually almost never do. But before I can explain how we deviate, I need to just define a simple random sample. So in a simple random sample, every entity in the sampling frame has an equal, independent, known, and non-zero probability of selection. Okay, so you have particular population size, and you randomly select, so many people from it. And so this is the baseline assumption that we have been taught with. And also, if you don't tell essentially whatever statistical package you're using what kind of sample you have, it's going to assume that this is the nature of your sample. Now, actually, generally speaking, the same, probably for any of you, if you're using some kind of secondary large data set, it will not have a simple random sample. Usually you have at least one of the following and sometimes all of the following types of deviations. You might have the need to weight elements to reflect unequal probabilities of selection. So going back here, note the terms that I bolded, equal and independent. Those are the two additional assumptions for a simple random sample. You can still have a random sample and violate those two conditions as long as you know the probability of selection. It doesn't have to be equal or independent, but if it's a simple random sample, it does. So sometimes we have unequal probabilities of selection, and I'll give some examples in a minute. Much of the time, especially for national surveys, we sample, instead of sampling individuals independently of each other, we first sample clusters at higher level units. This is usually due to cost concerns, and I'll explain that in a moment as well. And that introduces correlations between your observations, which violates the assumption of independence. Finally, this is one I find that most people know the least about, is you can actually improve the quality of your sample by stratifying your sample. That means, for example, if you know that you have a certain number of men and a certain number of women in your population and you can identify them, you can actually separate your lists of men and women and sample separately from them. That will give you the exact, at least for that gender variable, an exactly representative fraction from each group. Okay, so most large surveys use the multi-stage sample, as I mentioned. So let me give you the example from the Russian Longitudinal Monitoring Survey. So the Russian Longitudinal Monitoring Survey uses samples from about 40 regions. This would be called the primary sampling unit because it's not feasible to go to every single part of Russia to do a large sample. It would be far too costly. And then even within regions, you sample cities and rural areas so that you can send an interviewer basically to one city and have them cover multiple people rather than having to send them all over the place. Then we often sample within, in this case, our sample census tracts, then addresses, and then households. And I'll explain why in a few minutes. But the point is that you have actually 5 stages of sampling here. And so the probability of any, in this case, the lowest level unit is the household. That's what the RLMS's main sampling frame is. Its main goal is to represent households. Is the probability of the selection at each stage. Actually, the RLMS also actually has a sample of individuals. That would be the last stage, except that is a 100% sample. They try to interview everybody in the household. Whenever you use a multi-stage sample, you always will have clustering. That's by definition. You might also have unequal selection probabilities. So I'm going to give you a simplified example of what a multi-stage sample looks like and how it can introduce unequal probabilities and what can be done about it. So let's say, for example, that we have a population that lives in 10 villages. So it's 1,000 people. They're distributed among 10 villages. The villages have different sizes. Okay, so 4 of the villages have 50 people, 4 have 100, and 2 have 200. Now, if we were to draw a simple random sample, we wouldn't care what villages people lived in. It wouldn't matter for the purposes of drawing the sample. We'd have a list of our 1,000 residents, some kind of way of contacting them, and we would just randomly draw 100 respondents from that list. But let's say that we could only afford to go to 4 of those villages. We can only afford 4 interviewers. So we randomly sampled 4 villages and then sampled 25 people within each village. So our villages would be our clusters. And then that would give us our sample size of 100. But this will create both unequal sampling probabilities and underestimates of variance if we don't correct for them. There's 2 ways of going about correcting the first problem. First, let me show you what the problem is. So every village, if we have 10 villages, oh, I'm sorry, this is a mistake on top here. It should say every village's probability being selected is 0.4, 4 out of 10, because we're going to select 4 villages out of our 10. I apologize for that. Every individual's probability being selected is the product of the probability of the village being selected times the probability of the individual within that village being selected. And so what you can see happens here is that the people who live in smaller villages actually wind up getting higher probabilities of sampling, and the people who live in the smaller villages have lower probabilities. That's not desirable because we're interested in a sample of individuals. We're just clustering for convenience. And so if we don't do anything about this, what we're going to wind up is overrepresenting people from small villages. So you can imagine all the ways that could mess up your analysis. People who live in small villages probably are different systematically from people who live in larger villages. So if this is what we wound up with, we could correct for this by applying weights. So we could essentially say, well, these people are underrepresented, so I'm going to pretend that I'm going to basically count everyone from these villages as if they were 2 people instead of 1. And here I would do the opposite. I would only have them count for half a person each. So that's one way of handling it. But a better way is called a self-weighting sample. This is probability proportionate to size as a method to create this. Essentially what you want to do is you just want to do the math to get your sampling probability for the individuals equal. And it's sort of intuitive. The way you do that is you sample the villages in proportion to their size. So logically, if small villages have fewer people, these small villages should have a lower probability of winding up in our sample of villages, which is going to be used to represent our individuals. So we just basically, the way you do that is you just add to your formula the proportion, the number of individuals divided by the total population size, and that makes everything balance out. This solves the weighting issue, but clustering remains. So most, again, large-scale, high-quality surveys do this, and so you may wind up with a self-weighting sample, but you should never assume that. You need to always read documentation very carefully to make sure that that's the case. Okay, so 3 things that you need to know as the end user of data, and then I'll tell you about, I'll take a break for some questions, and then I'll tell you about a survey that I designed and show you some examples of how you handle this kind of thing. But you need to know, were unequal probabilities applied in the sampling procedure? And if that's the case, you need to be able to identify the sampling weights and apply them when appropriate in your analysis. The second thing you need to know is, were the sampling units clustered? If so, you want to find the variable that identifies what's called the primary sampling units. I won't go into the math, but basically, no matter how many stages of clustering you have, usually, in almost all cases, it's adequate to just adjust for the top level of sampling, because that's where almost all of the most serious clustering is introduced. And then finally, was the sample stratified? And if so, you'll have a variable identifying strata. Unfortunately, a lot of data sets don't make these variables available or make them hard to find. So, for example, the Russian longitudinal monitoring survey, sampling weights are easy to find. Primary sampling units, recently they started publishing a variable called PSU. Before that, you really had to do a lot of work to construct these PSUs. And it's still difficult. I haven't found a way to systematically identify the strata, but apparently they have done some adjustments, at least in the post-sampling stratification. I'm not going to go into the details on that, but anyway, usually you can identify these 2 things sometimes, but not always this one. This is less the least serious of the issues. So you always want to read your documentation very carefully. One other thing I want to just mention is that where people get confused about sampling is sometimes data sets have multiple sampling weights. And that will be because some complicated data sets, especially those that are carried out over time or across multiple populations, will have separate sets of weights for different subpopulations within that broader data set. So, for example, you might have different kinds of unequal probability selection issues at the household level versus the individual level. So for data sets that have both individuals and households, you will generally have 2 different types of weights. And so it's your job as a researcher to figure out what's both your unit of analysis and the population that unit of analysis is representing, and make sure you're using the appropriate weight. Another issue that comes up is with time. Again, with the Russian longitudinal monitoring survey, some of you may have come across this, that they both have cross-sections. A cross-section means you interview a population. It's just a representation of a population at one point in time. They also track people over time. Some of those people move, and since the actual sampling frame is addresses, not individuals or households, when people move, those movers should not be considered part of the cross-section. So what they'll do is, in the cross-sectional data sets, they'll give a weight of 0 to those people. So the point being that if you're using the RLMS and you only want to do analysis for 2011, and you want to claim that your analysis is representative of the population in 2011, if you've included all these extra people that are movers out of the sampling frame for neglecting to apply that weight, you're going to have very biased errors, a lot of bias, which will essentially, because people who move are very different from people who don't move. You only would want to use those movers when you're doing longitudinal analysis, looking at people's changing over time. Okay, so before I get to then what we're going to do about this in a particular specific example, let me just stop and see if there are any questions at this time.
Okay, we have a few questions, but they're more general. They're not really on the specific subject area. Do you want to take a general question right now, Jane?
Why don't we wait then until we get to the end?
Okay. Does anyone else have any specific questions on the material we've covered so far? And please do not be shy.
If you didn't understand something, point of clarification, this is a good time to ask.
We have one question. Could you describe self-weighting in more detail?
Yeah, essentially self-weighting just means that by design, even though the survey had multiple stages, the end result is that you wind up with equal probabilities of selection of your final sample. So it essentially means if you have a self-weighting sample that you can, it's as if you had a simple random sample from the perspective of probability selection. So you don't have to use sampling weights in adjusting your analysis if that's the case. That doesn't mean you don't have to pay attention to survey design at all, because you still have the issue of clustering and needing to adjust your standard errors.
And we had another question. One of the people in the audience had a difficulty with their internet, and she asked if you could just quickly summarize stratification for her.
Okay, stratification. Actually, why don't we just wait till I get, because I'm going to come back to it since I don't have to repeat it for everyone, but I'll get to an example.
Okay. And we had a question from Dimitrios, but Dimitrios, we're going to save your question and get to it at the end of the webinar, okay? And that's all for now then, Jane.
Okay. All right. Okay, so I'm going to tell you essentially the quick and dirty way of just, if all you want to know getting out of this is what do I do with, my data set that I got from, some secondary source. I'm going to only tell you about Stata, but, all the other major software packages have more or less equivalent routines. Stata does have by far the highest quality suite of survey adjustments. Again, I don't have time to go into the details, but there are some limitations to the others like SAS and SPSS. If anyone wants to know the nitty-gritty of that, I can send you some references. But for most of what most of you are doing, it probably won't matter. Okay, so essentially, but the nice thing about Stata is you can tell Stata the features of your data set sampling design one time by using this procedure called survey set. And then whenever you want to apply that sampling design to adjusting any analysis, you just use the prefix SVY colon, and then whatever, regress, X on Y, or whatever your command you want to do is. The SVY subcommand doesn't work on every statistical routine data, but it does on most of them. And so that's nice that you don't have to every time remember what these variables are doing and remember to apply them. All you have to remember is just to do this and then use the SVY prefix. I should mention that this is, I can't remember when it changed, but I think it was this particular syntax was introduced maybe in Stata 10. So if you're using an earlier version of Stata, it's a little bit different, and you'll have to look at the documentation, but there is something equivalent. I should also just mention that there are alternative ways of doing adjustments in Stata where you do it within the command. So you could just you can type a res x y x comma, and then there's cluster subcommand. That was the old way of doing Stata for those of you who've been using it for a while. Again, I don't have time to go into why, but generally speaking, the new way is more accurate. So it's better to do it this way. And so remember I mentioned that you want to be able to identify, to the extent they're relevant, these three variables. So the name of the variable may be different, okay? So in your data set that you get from somebody else, they might not call the weight variable weight. So for example, in the Russian longitudinal monitoring survey, it'll be something like, RSAWHT PW or something like that. I mean, they have different abbreviations and prefixes depending on the round and whether we're talking about individuals and households. So you have to look at the documentation. Okay, but now the other thing is that a lot of times we don't have all three of these, and that's okay. It's not that you're not required to have all of these. You could just put the weight if all you have is a weight variable. You could put the PSU in the weight if you have the two of those, whatever you happen to have. I'll also just mention that if you look in the documentation for sampling for Stata, it's like an entire manual. There's a lot of other esoteric things that we won't discuss today and won't come up for a lot of what you're doing. The other thing I was just mentioned that things like I'm sorry, this should be replicate weights, not rates. Replicate weights are becoming very common in Western large-scale surveys. It has basically the purpose of it is to preserve confidentiality. I've never seen it so far in a Eurasian context data set, so I won't talk about it now, but I'll imagine that it'll be coming pretty soon. The reason is that it's just more complicated technically, and until recently software couldn't do this kind of thing anyway. Okay, now let's focus now on the issue of unequal probability by design. Why would we have that, first of all? Sometimes we do this on purpose. We want, for example, to oversample a relatively small group. Because if a group is only, say, 2% of a population and we have a sample of 1,000, we're going to wind up with, on average, 20 people. That's not enough to really say anything about that smaller group. But the thing is, since that group is oversampled, if you don't, when you're analyzing the full population or the full sample, if you don't let your statistical package know that you have more of whatever your subgroup is than is true in the population, then they're going to wind up having an inordinate weight in the calculation for the overall group. And again, I'll show you. I think this will hopefully be clearer to everyone when I give some examples. The other reason is to correct for sampling procedures themselves that lead to unequal probabilities that are not necessarily desirable, but were just necessary for the purposes of cost control or something like that. For example, we often use addresses as the basis for finding individuals, but we don't actually know how many individuals are at each address, leading to differences in the probability of individuals being selected. And again, I'm going to give a detailed example in a couple minutes. The other reason is to exclude individuals who should not be included for particular subpopulations, like the RLNS example I gave, so those would be 0 weights for those people. And for all of these, if you don't correct for it, your estimates will be wrong for any variable that is correlated with whatever variables were essentially determining the unequal weights. So if we have unequal weights based on household size, so if people live in small households are overrepresented, then that means we're going to have wrong estimates for any other variable that's correlated with household size. So for example, marital status would be a good example of that. So let me just give an example of an unequal probability to get at a subgroup. There's a very interesting survey called the Soviet Interview Study. This was done before Western researchers could go to the Soviet Union to do samples. So there was a sample, the target population was all Soviet emigres to the U.S. who arrived in this particular area. And so that was, they knew that this was not a good representation of the Soviet population, obviously, because emigres were not representative. But it was a sector of Soviet society that the survey respondents could represent. So basically, the adult European urban population were those that were really going to be represented in any reasonable numbers for making inferences. They had a pretty good list from, this was basically based on visa, people couldn't come here very easily without visa support, that kind of thing. So they had this list, and they also had the ages of the people, so they sampled from that. However, they had an oversample, actually of 100%. They interviewed all non-Jews, or they tried to anyway. They selected all non-Jews into the sample. That's because Soviet immigrants were overwhelmingly Jewish to the United States. And so, but they wanted to also be able to say something about non-Jews, and if they hadn't oversampled, there just wouldn't be enough cases to make inferences about them. Now I'm going to give you another example from the first survey that I designed, which was for my dissertation. This is Kaluga Consumption City. Kaluga is just a city in Russia where I did my field work. And so I wanted to do a sample of just adults living in Kaluga. That was my population of interest. But there was no sampling frame of individuals available. There was no list of people living in Kaluga with ways of how to find them that was reliable. Actually, there were lists of people, but they were very problematic because the lists were based on where people were registered. Propiska, for those of you familiar with that system. I would say, at least based on my experience, and I'm actually I do a lot of research on housing now, probably at least a third of the people in Kaluga were not actually living where they were registered. So it wasn't a useful sampling frame. So instead we used a list of addresses. But we also didn't actually have a list of addresses, so we had to create it. So I'll get to that in a minute, how we did that. But we have our list of addresses. We randomly sampled one person from each address. And so we have, let's say we have 100,000 addresses. This is not actually the case, but for sake of simplifying, sorry, this would be 1,000, not 100. That's a typo. But if we get a simple random sample of all those addresses, then we would have a 0.01 sampling ratio, 1,000 people out of or 1,000 addresses out of a population. I'm sorry, 1,000 individuals out of a population of 1,000. So, but we don't have that list of individuals. And so if we have to then sample. The second stage of sampling is within the household. So usually how this is done is you use a random generator of some kind. You get a list. The interviewer goes to the address, knocks on the door. Hopefully someone answers the door, and you ask for a list of all the people who live there. And then you randomly sample from that list. And there are various ways of doing this. One common way is whoever has the next birthday. But the thing is, if somebody lives alone, then they have, given that their household is sampled, then they have a 100% chance of being sampled, so it's just 0.01 times 1. But if somebody who lives with somebody else, if there are two people, then they only, once their household is sampled, there's only a 0.5 or 1 out of 2 chance of being sampled. So what winds up happening is adults living in larger households wind up being unrepresented, and conversely, people who live in small households will be overrepresented. So why did I decide to sample addresses rather than individuals, knowing that this was the case? And it's because I didn't have adequate list of addresses. And I just want to say a few things about quality control issues that come in, and they're very common if you're ever dealing with, this is not just the case in Eurasia, by the way. Market research firms in the United States often use what's called the random walk method, and it's very, very common also in Eurasia, even with the highest quality, non-commercial firms, university-based survey research firms and stuff, because it's cheaper. What random walk means is you give an interviewer a random, quasi-random place to start. You tell them, stand on the street corner and walk down the street and choose every third house, building, and then within the building, choose every 7th apartment. This is very problematic for a couple of reasons. One is it's prone to even just sort of innocent interviewer error, where it's just sort of complicated for the interviewer to follow those instructions. The more serious issue is that it lends itself to sort of cutting corners on the part of the interviewers. So, it's in theory what they're supposed to do is if nobody's home at the address that they randomly select upon the random walk, then they should list that as a non-response and then have to go back again or have it just considered a non-response. Instead, what they'll often do is they'll just, think, well, it won't do any harm if I just knock on the person next door. But it actually does a lot of harm, because the problem with doing that is you wind up with overrepresenting the kinds of people who are likely to be home. Older people, stay-at-home mothers, people who are ill, unemployed, which will screw up just about that's going to be correlated with almost anything that social scientists tend to be interested in. So the highest quality surveys do not use the random walk method. Where I learned about the alternative was actually through the RLMS. So instead what they do, and what I did, is to enumerate addresses. You actually have to pay somebody to walk up and down the streets and go to the apartment buildings, count the number of apartments, write down all the addresses to get a list of the addresses that you can sample from. But it's not practical to do that for the entire city, so we used a multi-stage design first to select basically neighborhoods. So this is getting into our clustering. That helped with quality control, but it still didn't help with the issue of the fact that we didn't know the household size before we selected the addresses. There was nothing we could do about that. So by design, I was going to have unequal sampling probabilities. So let me show you the effects of this. Now I'm going to escape from here and go into Stata, where I've got my data set loaded. And so I'm only going to tell Stata right now that I have I have unequal probabilities of selection in my sample. Oops, yeah, and that this is the name of the variable that I'm going to use. This is PW means probability weight. There's other kinds of weights that I won't discuss. This is mostly what you're going to want to use. So I'm just telling Stata that this. Sorry, just wait. Typo. My weight variable in this data set is conveniently named weight. Okay. This stuff is all just, we can ignore right now. It basically means that these are the defaults and that we don't have strata or PS or stratification or clusters in this, at least in what I've told it so far. Okay, so the easiest way to see the effects of this is I can estimate the mean number of adults in the household. Okay, so that's my variable for the mean number of adults. It's telling me there's an average of about 2.1 adults. Now, I'm just going to take a minute for you to just think about, before I show you the answer, what is going to be the likely effect of not adjusting for sampling design? If we know that smaller houses are overrepresented, what will that do to our estimate? And the way we can find out is to use the survey command. It's going to apply my sampling weight, and this is what you would expect, is that if we're overrepresenting small households, that's going to pull down our mean estimate, right? So if I forgot, so the true mean household size in the sample, or in this population, assuming that we have a good sample, is about 2.5. So that's a pretty serious error. I mean, that's on the order of 25% difference in my point estimate if I don't make the adjustment. So you can imagine how this can really, now one take-home point here is that adjusting for sampling weights matters the most when you're doing descriptive statistics. That is, you're just trying to describe the population. Okay, it's less egregious if you don't control for weights when you do things like regressions. If we have time and someone wants to know, I can try to tell you about why later. Suffice to say that in the most modern versions of software, you have nothing to lose by just adjusting for your sampling weights at all times, including when you're doing regressions. But if you don't do it when you're just trying to get descriptive statistics, you're definitely running the risk of grave errors. And for those of you who are sitting there thinking, oh my gosh, I can't believe I've been making this mistake all this time, I taught this workshop to, I've taught it to, well, many quite far advanced graduate students and assistant professors in various contexts who were horrified to realize that they've been making this mistake. So, you're not the only one if that applies to you. Okay, so you'll also notice actually that both the mean and the standard error change. And again, I'm not going to go into why right now, but generally speaking, when you have one problem, it also leads to the other. Okay, so now let me just give you another example. Let's think about marriage. So this is just a dummy variable for, this gives us essentially the proportion of individuals, I'm sorry, this is a sample of individuals, the proportion of individuals who say they're married. Now again, think about what would it do to this statistic if we don't adjust for our survey design. Okay, same idea. Well, obviously people who are living alone, who are the most overrepresented, are unlikely to be married. And so that's why it's dragging down our estimate. This is the correct one. Okay, so let me now move to the issue of, I'm going to skip this just because of time, but you could do the same thing with a regression. Okay. Okay, now what about sampling design and standard errors? So I mentioned earlier that there are sort of two ways that we can wind up with deviations. Clustering will usually increase your standard error. In other words, if you don't adjust for it, you're going to be overconfident. Your confidence intervals are going to be too small. Stratification, on the other hand, usually decreases standard error. It makes the quality of our samples better. So, and then if we don't adjust for it, we're going to be underestimating our standard errors. I'm sorry, overestimating our standard errors when they really should be smaller. The way that I like to think about this is the term effective sample size. So, you know that in any, estimate of standard error, the n comes into the equation. The larger our sample size, larger our n, then the smaller should be our standard errors, because the more confident we can be in our estimates. So the effective sample size is what n would we need to have for a simple random sample to have the same degree of standard error as is the case in our complex sample. So, if we know that our clustering is essentially decreasing the quality, our confidence in our survey, we would need, relatively speaking, a larger sample for a clustered design to get the same statistical power as if we had a simple random sample. So, simple random samples essentially are more efficient from the perspective of you can have a smaller sample size. However, there are cost trade-offs. Generally speaking, you're still better off doing clustering and having a much bigger sample size to account for that, still going to be way cheaper than trying to somehow get even an adequate sampling frame, let alone sending interviewers all over the country. I mean, I'm using, population survey, population countries as my example here, just because it's what's the most common that people use, but you could say the same thing about organizations. Whatever your sampling unit is, it's still often easier to do some kind of clustering. Okay. So
Jane,
why does this cause us? Yes. Mm-hmm.
Can you go full screen?
Oh, I'm sorry. Yes. Thank you. Sorry about that. Just got me back to the.
That's the downside.
Yeah. No. That's good. It's okay. So, so the effects here are that, basically that people who live in the same neighborhood, which is usually what we're talking about primary sampling units for population surveys, or the same region, wherever, tend to be more similar than people in others. So that causes us to have the false impression that people are more similar to each other. That is, that there's less variance in our population than is true in reality. Okay, so this was the case in the Kaluga survey, and there was some severe clustering in my sample. I was a graduate student, didn't have a lot of resources. Generally speaking, you don't want to have clusters with 40 people in them if you can help it. It's better to have smaller. So again, we're sort of running a lot of time, so I'm just going to kind of cut to the chase here and show you an example here of what this would do. So here, I'm going to use a variable that I know is probably correlated heavily with the region, which is whether what kind of housing people are living in. Okay, so this is suggesting that in Kaluga, 9% of people live in dorms. Okay, that's the mean. Okay, and then it's also showing me this particular standard error. We have 2 issues here. So I've only surveyed set so far. I've only told data about my my weighting, but I haven't told it about the clustering. So here we can see, as we would expect, that actually the correct estimate of the mean is smaller because we have some overrepresentation of dorm dwellers. That's based on household size. They tend to also have smaller households. But there's another issue, which is the variance. So now I want to do my survey set command. I need to redo it. Every time you do this, you can just will reset what you have. So PW equals weight, but then I'm also, the syntax is you put your, it's a terribly designed syntax. I don't know why they can't make it more intuitive, but basically you just put the PSU variable kind of on its own right here. In my case, I called it site. Okay, so now I'm telling it that I have both a clustering and weighting. Okay, now I'm going to rerun my command again, and I should get a different standard error if I've done things correctly. And you can see that I do. On the order of, twice the size, more than doubling. Okay, so I've severely underestimated my standard errors if I don't adjust for the fact that I have a lot of clustering in my data set. And again, it's not just our estimate of dorm dwellers that's the issue here. Anything else that we think is correlated with people who live in dorms, except they're more similar to each other, and there's a lot of ways we can think about that. I mean, again, in the Soviet Union, it's not just students, or the post-Soviet era as well, but students, but also people who haven't managed to get independent housing tend to be much more likely to be working class. So there's a lot of reasons this is not a good thing to not be adjusting for these standard errors. And again, I could do a regression, and I'm not going to do it now, but if I did a regression, I would also see the same kinds of issues where my regression coefficients would, especially the standard errors, will usually go up dramatically when you have this level of clustering. In really large samples and where the clustering is not severe, that is, there are not that many people in the same primary sampling units, then it may not actually matter that much. But you should, there's no reason not to do these adjustments. I'll just say that quickly that, one reason I think that we haven't learned about this, it's actually generational. Maybe those of you who are the youngest in this audience, I'm willing to bet, are more likely to have learned this stuff in graduate school, because when I was in graduate school, well, there was no point really in learning about it because you couldn't do anything about it. You might learn about it theoretically, and that's how I learned about it, because I did statistics courses as well in the stats department, but the software couldn't do much about it. Now that's not true anymore. So this is stuff that's easy to deal with, and we might as well. You're more likely now also to get slammed by reviewers if you don't do these adjustments, again, because people know now that this is doable, and so let's do it. Okay, so I'm going to wrap up, I think, in a couple minutes. Let's just take about 5 more minutes to say, I wanted to say a little bit about stratified samples. And again, just because of time limitations, I'm actually not going to run a statistical example here, but I'll just tell you the idea behind it, which is basically if you know in advance, let's say that essentially there's a variable of interest that you already know in advance what that variable is for each member of your sampling frame. So in the case of region, that's easy because we know what regions we're going to be sampling from. And so it's very common for surveys to stratify by region. In fact, that's what the RLMS does. For example, they first decide how they divide the country up into regions, north, south, east, west, but a little more complicated than that. And then they know, based on census data, about how many people are in each of those regions and how many would be associated. And then they just sort of, based on their proportion in the population, decide how many they're going to select from each region. And what that winds you up with, what that does for you is that it eliminates the random error in the distribution for that particular variable. You can make your proportionate numbers of people or whatever your analysis is within each strata exactly match the population to the extent that you have good data for that particular, what we call stratifying variable. So the term is confusing because most of, stratification, we're not talking here about inequality, in sociology or something like that. We're talking about just dividing up a sampling frame based on information we already have about the nature of that sampling frame. So this is I got from a textbook, but I think it's an easy way to see what this means. So let's say that we have we're just doing a sample of faculty in a university, and we know what the population of the faculty is. It's not hard to go and get a count of how many faculty are in each division of the university. Ignore the middle column for now. Look at the hypothetical simple random sample. Well, every time we do a simple random sample, we're going to get a little bit different numbers, right? We're not going to get exact percentages across these divisions because there's random error every time we draw a sample. But if we stratify our sample, we can say in advance that based on the sample size that we want to get, which is what I can't remember now what the sum of these numbers is, but we've determined in advance that we want a sample of, I don't know, it's like about 1,000 to me, or 800, something like that. We can just then look at what is the, actually we can see here it's 450, there's total on the bottom, sorry about that. Okay, so we have 450 people that we want to sample out of 9,000. We can just calculate the sampling fraction. We can say, well, if 1,800 out of 9,000 is the population ratio for humanities, then we should have 90 out of 450 for the humanities. And so we can just, essentially it's like drawing 5 separate samples. You first draw your sample of 90 from the humanities faculty, then you draw your sample of 60 from the social sciences faculty. And that by design gives you a perfectly balanced sample for that variable, not necessarily for other things. So this only has any effect on the things that you're stratifying on. Again, I can't get into why now, but you generally don't want to stratify on too many variables at once because then you'll wind up with like a lot of categories where you only have 1 or 2 people or individuals that even fit them. If we were to do pure sciences, and then also add gender and race, you're going to wind up with just a few in most universities. Let's say non-white men in the United States anyway. So the point is that if we did a simple random sample, what we would hope to get is something that's as close as possible to this. But we're actually going to get something more like this. So this is better. A stratified sample is better, and therefore, logically, we should have our standard errors, our standard errors should go down if we adjust for the strata. Because if we use stratification, we have a higher quality sample, other things being equal, than a simple random sample. So that's a nice thing. And if we know about it, we can adjust for it. It means that we can be more confident in our results. Okay, so I'm actually moved, I realized, to the non-response that we're not going to have a lot of time for, but I just want to say quickly on this that there's a lot of other kinds of adjustments that you might find in secondary survey data. Let me just say, use extreme caution in trying to do this yourself, okay? So what post-survey adjustments means is, let's say that we know that we had, let's say we did this stratified sample. We know exactly what our sample should look like when it comes to faculty and their colleges. But not everybody answers the survey. Let's say that the people in the, let's say in engineering are more likely to travel and have other consulting gigs, and they're just harder to track down. So let's say we wind up with, in the end, can't get all those engineering faculty samples to respond, so we wind up with them underrepresented. Well, we could then construct weights to say, well, even though we only managed to, interview, 60 engineers, we should have had 110. So we're going to count them, those that we did get, as if they were worth almost 2 people. That's called post-stratification weighting. Same thing if we, for other reasons, we know that people are missing, even if we didn't stratify for them. Let's say that we know that this happens a lot, that women are more likely to respond to surveys than men. We know from census data, even though we didn't stratify our sample this way, we know that that there really should be 53% of women, not 60%, let's say in Russia. And so we can adjust the weights. But if you don't know what you're doing, you can really screw things up. So, in a professionally issued survey, again, you read the documentation, look for whether or not they adjusted for non-response, how they went about doing it, and some of their weight, they might issue the weights with and without these post-survey adjustments for non-response. And so again, that's why sometimes in some data sets you'll wind up with like 20 different kinds of weighting variables. It can be really overwhelming. So my hope is that after listening to this webinar, at least you'll have some idea of what to look for if you do run into that situation. So I'm going to wrap up there. I know that this is throwing a lot at you without a lot of detail, but my goal is to give you an overview, and I'm happy to answer your questions now.
Okay, you guys can continue sending in questions, but we have a few here now, so let me just get those to you, Jane. So we have one question.
Okay.
Does clustering work if a given unit or cluster has very few observations? For example, if there's fewer than 5 or even just 1?
Yes, that's a good question. Okay, so does clustering work if it only has a few? Well, the way to think about it actually is, in a simple random sample, you can think about every individual as a cluster of 1. So it can work. It's just that, so I guess there's 2 ways to think about it. Ideally, the smaller your clusters, the higher quality your results are going to be, because fewer of your observations are correlated with each other. The more correlation based on the sample design we have between our observations, the larger our problem is with overestimating the homogeneity of our samples. So ideally, you could have, clusters 2, 3, 4, that'd be fine. Now, I think the other way that we get into this, though, usually that's not feasible. And in fact, if we could do clusters of 1, then we're back to a simple random sample. It's the same thing. The other time that this can come up is if we do the probability proportionate to size. But that solves the problem too, right? Generally speaking, you're going to want to have clusters that are the same size at the lowest level units. So did that answer the question? Or I'd like to have her person follow up.
If you have any follow-up questions, just let us know. Okay, nothing yet, so we can move on. So we had a general question from before, and this question is a question on quantitative versus qualitative research. And this question is, why is the distinction between quantitative and qualitative research so important, and can't we use both types? So it's like a general research method.
Yeah, so the purpose of this particular webinar series is to encourage higher quality use of quantitative methods in Eurasian context, and that's based on the goals of the program and its funders. I personally use a lot of qualitative methods. I'm completely agnostic about qualitative versus quantitative. I think it all depends on what you want to know and also what is already known. So to just give an example from my own work, I just wrote a book about housing in Russia, and it was almost all based on qualitative in-depth interviews because so little was known about the things that I was interested in. I was particularly interested in the cultural meanings of housing, a place of your own, living with your parents, mortgages, the kind of stuff that just had never appeared on survey. So I kind of beat to death what was possible with the Russian longitudinal survey. So there is work, I did do statistical analysis of what I could do to get at the sense to analyze, what are the contours of housing inequality, but that's not going to tell me anything about how it affects people's everyday lives. Having done that, I now have funding to do a new survey to test hypotheses that came out of that qualitative research. But I would only have been able to get that funding and formulate a research design and questions that are appropriate because of having done that qualitative research. So in my own work and when I'm training students, I think that you should let your research question drive your method and not the other way around. So the unfortunate thing about constructing a webinar series this way is we're focusing on the method, not on the research question. But that's also necessary given the holes that we have in training, particularly for people who are working on the region that we all have in common, that have training in lots of different fields that may be coming to quantitative methods. For example, anthropologists often come to quantitative methods with no formal training because on the ground they got interested in something that they then realize a survey could help them answer, but they don't know how to do it.
Okay, here is another question. Suppose you know that your sample was biased. For example, certain ethnicities were overrepresented in the survey and others were underrepresented. What could be done about it?
Yeah, so this is actually what this last slide is about. So let's just look at the example on this. So you mentioned ethnicity, but we could also talk about urban versus rural. If you know a priori what the population ratio should be, and that's the big if, right? So the question is, how do you know how many of a particular ethnicity should have been in your sample? The only way you can know that is if you think you have a high-quality census. So if you have a high, it's actually fairly simple to calculate those weights. I mean, to give the extreme is, let's say that a minority group was underrepresented by 50%, only half. Let's say we know they're 20% of the population and somehow only 10% went up in our sample. Well, essentially what you just do is you weight by the ratio of what should be in the sample to what appeared in the sample. So this would be 2 to 1. So you would essentially want to count each of your individuals that were of that minority group as if they were 2 people. Where this can get hazardous, though, people often do this without actually having good information about what the true population estimate looks like. I mean, that's probably why we do sampling a lot of the time, is that we don't know what our population looks like. But that's what you can do about it. The other thing that you can do, again, is earlier in the process, is where you just try to have a higher quality sample to begin with. I mean, that's what we really hope for. What you really want to do is try to make sure you have as truly random a sample as you can and increase your response rates as high as you can. And this is actually a topic that I was thinking about doing for a follow-up, and you're going to get a survey after this with a list of questions of possible topics that will help me decide what to do next. But one of them is exactly what do we do about non-response and missing data, both in the process of collecting data to minimize it and also after the fact. Also, in a handout that I prepared that Denise is going to send along with the survey, I have some references to textbooks that can help you with that as well. It's a very good question.
Okay. Another question is, are there data sets from Central Eurasia that are better or worse at providing the sampling information that you would use to do these adjustments? So there's some surveys that are better or worse to work with data sets.
Well, generally speaking, some of it is you have to look at the source. So, think organizations, so I'm speaking from the perspective of an American researcher. I know there are a lot of people on the call from other parts of the world, so it really would depend on the country context. So, for example, in Russia, which is mainly where I work, anything coming out of the Higher School of Economics, Demoscope Lab, or the Levada Center, generally speaking, has pretty high quality both survey techniques, but also providing the data that goes with it that you need, to the end user. Also, like the gender and generation surveys, this is a multi-country survey with lots of funding from lots of different sources, and they also provide the information. So in terms of lower quality, that's going to often be for two reasons. One is that this is sort of the most troubling cases, is where the people who actually collect the survey itself aren't well trained in these issues. And so, for example, they use quota samples, which a quota sample is when, again, you know that, let's say I know that my population is about 50 men and 50 women, so I'm like, well, I'll just go out and find 50 women and 50 men that I happen to know. I mean, that's oversimplifying. There are some good rationales for doing quota samples. I mean, especially with internet polling becoming more and more accurate. There's an interesting debate in statistics about this. But since that debate hasn't really gotten into the sort of formal methodology of social science research yet, the best practices for that, I should say, and because what I'm talking about now is in the context of assuming you want to use probability theory. If you're going to use probability theory for calculating your inferences, you've got to have a probability sample. There's no ifs, ands, or buts about that. So if people aren't, so there's the issue of who's collecting the data, and then there's also the issue of the expected user. And so the other problem can come is when maybe these kinds of techniques were used, and there was a sampling expert who designed the sample, and there was good quality control, but they don't release these variables that you need to the end user. Then there's nothing you can do about it. So I mean, I don't want to call out and embarrass anybody. I just gave you the examples of what I think are the highest quality ones. You know how you can tell is look at the documentation of the survey you're using. If they say nothing about, even if it was a simple random sample, the documentation should say that, right? There should always be a section on the sampling design, quality control procedures, and also the variables used. Now, one thing that you can also just try if you ever come across this, so I'll just give an example from my early use of the RLS, because I've been using it since, I think, 1998. They didn't used to release the PSU data. I don't think they think that anybody cared about it, and they were worried about confidentiality. So I had to ask for it. And when I asked for it and explained why I wanted it, they gave it to me, after I signed some stuff about confidentiality. And I'm sure I wasn't the only one, and now it's worked its way into the public release versions of the data sets. So, you really don't know until you look at the documentation.
Okay. One of our attendees would like to know more about the effect of these issues on regression analysis. So I don't know if we have time for an example, but if you could just maybe summarize the effect on the regression analysis.
Sure. I think we might have time for an example.
Okay. Sure. If you would like to.
For a second, and find the sample code that I would have shown. Sorry, just one moment.
Sure. One of the other questions, just because I can answer it, is someone was asking for recommendations on textbooks, and like Jane said, we'll in her handout that I'll be sending out, there'll be a list of the textbooks that you could look at. Someone else was asking about the date of the next webinar. Now that you've registered for this one, we'll be sending you information about all future webinars. And the last person asked about being able to look at the slides. We're going to post the recording of this presentation along with the PowerPoint and the handout on our website, and I'll send you the link, and that will hopefully be later this week.
Okay, so let me go ahead and do an example from my consumption survey about this. Well, let me first explain why for the actual, well, sorry, let me show the example first, and then I'll tell you more about the theory. Okay, so one of the many sort of miscellaneous questions we asked about was how often people ate fruit. Okay, this is in 2002, which is when the economy was still not great in Kaluga. And being able to eat fruit frequently was pretty luxurious. So, and people generally considered that it was desirable. Almost everyone wanted to eat fruit at least several times a week. Most people couldn't afford to. Okay, so this gives you a sense of the distribution. Now I have not adjusted for my sampling design here, right? Now I'm just giving you the mean, and then I'll show you the regression, but just to see what difference it makes even for the mean. I'm not sure that it makes that much difference, but when you do it this way, it sort of gives you proportions, but it's the same idea. So actually, in the true population, it looks like maybe it's a little bit it's not that different. There's a little bit difference in the population distribution, but not much. Okay, but for the, now let's try a regression. Okay, so what are some things that might predict the frequency of eating fruit? Well, clearly income could be one. So again, this is not how you would ever want to do a real regression because I'm not adjusting for various things, but just to keep it really simple. Okay, so this is showing me that, and again, this is the units here. You can't really overinterpret this, but it's showing a statistical significant association between household income and the frequency of fruit eating. Not surprising at all. Now I haven't adjusted for my sample design here. Now I could try again. Oops, I need to regress here. Okay, so, and I'm going to do it one other way actually. I'm going to take away the clustering information. Okay, unfortunately this is going to scroll off here, but what you can see is that, did that not work? Oh, it did, it did. Okay, well let's first look at this one. This is like correcting for everything. So we've corrected for our weights, okay, and for our standards. And you can see that the standard errors go up. Now again, it's not enough to matter because it's such a highly significant, coefficient that, but you can still see the direction of change, right? The thing is that when we only adjust for the weight, but not for the standard error, as you would expect, the point coefficient is the same because the weight is what takes care of the coefficients, okay? But the standard errors have not, and the other thing, I mean, I can't even remember why now they're actually going in is it a different direction here? Yeah, when you only adjust for one part of your sampling and not the other, you can wind up with some strange directional effects. So this is the correct version. Okay. So now on the point I made earlier that it doesn't matter as much for coefficient as standard errors. I'm trying to remember. I think if I give you some more variables here, the other thing that really affects fruit eating is age, and also higher education, or that we have fewer things that could affect it. So I'm just going to throw in some other variables. Just do this first. Regress, fruit, and it's curvilinear possibly, so I'm putting a square term in there. Let's just throw in the rest of these. Okay. All right. All highly significant. So again, I'm not sure that we're going to get any action here. Now we do. And again, we see some changes in our standard errors, and the magnitude of the change in the standard errors is typically much larger than the magnitude of the change in the coefficients. And the reason is as follows. I wish I had a way of drawing easily on here. I think I can make it. How much time do we have? Let's see. Okay, I've got time to do this. I'm just going to draw. Do I not have time to do this?
You do. I think on the control panel you might have a little highlight tool.
No, what I want to do is draw like a little,
oh, okay.
like a diagram.
I
but I'm going to see if I can do it real quick here. Okay, ignore the direction of the arrows here. This is just like my x and my y axis, right? Axes here. Okay. All right. So this is, imagine that we have a regression. This is the predicted regression slope. Okay. So this is the effect of age on fruit eating or something like that. Okay. Now, the reason that usually having, if you have cluster, if you have unequal probabilities of selection, let's say that this is age, and for whatever reason we wind up with an over-representation of old people in our sample. But other than that, we don't have bias, right? We just have more people of that age than this age. We don't have any bias in the degree to which the people who wind up selected here are more or less likely to eat fruit. In other words, we just wind up with more points around here than down here. So in a nicely distributed diagram, we'd have just, kind of a lot of random points along here without any, gaps. But let's say that middle-aged people just didn't answer as much. Well, we'd have sparser data here. But we'd still have, as long as we didn't have bias in the measurement of this association. It's not that the issue is not bias in the measurement. In this case, since we're not interested in, we're not trying to estimate, the number of old people or the distribution of age in general. We're not trying to estimate this or this. We don't care about the age distribution. We don't care about the distribution of fruit eating. What we care about is the association of one to the other. In a well-designed survey, if what you have the bias in the measurement of, in this case age, is not correlated with the association that we're interested in, it's not going to matter. You're just going to wind up with more variance, essentially. So I know that's sort of a little hard to see, and if I could do this again, I would have had a more explicit example here. But as long, when you get bias would be if you wind up with points that were way up here or something like that. But as long as they're all clustered along the true regression line, it doesn't matter if some of them are, there's more over here than would be in the population. So that's kind of the idea behind it. Again, it doesn't hurt to adjust for it, but like I said, it's the standard errors that generally are the bigger problem than the point estimates when you're dealing with regression type models or anything where you're estimating associations, relationships between variables as opposed to the distribution of the variables themselves. Any other questions?
Actually, that was the last question. So we can now thank everyone for coming. I'm sure that for many of the students and also many of the faculty who are here, this is a very busy time of year. So thank you for coming. As we mentioned throughout the event, we're going to send around a survey. We'd like to collect some of your general impressions on the event. And also, you'll be able there to let us know what are some topics you'd be interested about hearing or not hearing in the future, and also if the level was appropriate for you or not. So please do take a few minutes to fill in that survey. And now that we have your contact information, we will be sending you the announcements for all the future events, so don't worry about missing those. So a big thank you to Jane. So thank you very much, Jane, for this excellent webinar.
Thank you.
And with that, we will sign off. So good afternoon, everyone.